times x times y cubed over z to the 5th, the square root of z. I'm going to leave this example as is, but sometimes people prefer to rewrite radical expressions without radical signs in the denominator. That's called rationalizing the denominator. I won't do it here, but I'll show you how to do it in the next example. This example asks us to rationalize the denominator. That means to rewrite as an equivalent expression without radical signs in the denominator. To get rid of the radical sign in the denominator, I want to multiply my denominator by square root of x. But I can't just multiply the denominator willy-nilly by something unless I multiply the numerator by the same thing, so that I'm just multiplying my expression by 1 in a fancy form and I don't change the value of my expression. Now if I just multiply together numerators, 3x square root of x, and multiply denominators, square root of x times square root of x is the square root of x squared. Square root of x squared is just x. Now I can cancel my x's from the numerator and denominator, and my final answer is 3 times the square root of x. I rationalized my denominator, and in the process, got a nicer looking expression. In this video, we went over the rules for radicals, and we simplified some radical expressions by working with fractional exponents, pulling things out of the radical sign, and rationalizing the denominator. This video goes over some common methods of factoring. Recall that factoring an expression means to write it as a product. So we could factor the number 30 by writing it as 6 times 5. Or we could factor it more completely by writing it as 2 times 3 times 5. As another example, we could factor the expression x squared plus 5x plus 6 by writing it as x plus 2 times x plus 3. In this video, I'll go over how I get from here to here, how I know how to do the factoring. But for right now, I just want to review how I can go backwards, how I can check that the factoring is correct. And that's just by multiplying out or distributing. If I distribute x plus 2 times x plus 3, then I multiply x by x, that gives me x squared. X times 3 gives me 3x. 2 times x gives me 2x, and 2 times 3 gives me 6. So that simplifies to x squared plus 5x plus 6, which checks out with what I started with. So you can think of factoring as the opposite of distributing out, and you can always check your factoring by distributing or multiplying out. A bit of terminology: when I think of an expression as a sum of a bunch of things, then the things I sum up are called the terms. But if I think of the same expression as a product of things, then the things that I multiply together are called factors. Now let's get started on techniques of factoring. When I have to factor something, I always like to start by pulling out the greatest common factor. The greatest common factor means the largest thing that divides each of the terms. In this first example, the largest thing that divides both 15 and 25x is 5. So the GCF is 5. So I pull the 5 out, and then I divide each of the terms by that number, and so I get 3 plus 5x. Pause the video for a moment and see if you can find the greatest common factor of x squared y and y squared x cubed. The biggest thing that divides both x squared y and y squared x cubed is going to be x squared times y. One way to find this is to look for the power of x that's smallest in each of these terms. So that's x squared. And the power of y that's smallest in each of these terms is just y to the 1, or y. Now if I factor out the x squared y from each of the terms, that's like dividing each term by x squared y. If I divide the first term by x squared y, I just get 1. If I divide the second term by x squared y, I'm going to be left with an x and a y. I'll write this out on the side just to make it more clear. Y squared x cubed over x squared y, that's like 2 y's and 3 x's on the top and 2 x's and a y on the bottom. So I'm left with just an x and a y. So I'll write the xy here, and I factored my expression. As always, I can check my answer by multiplying out. So if I multiply out my factored expression, I get x squared y as the first term, and the second term, I get x, they're now, let's see, 3 x's multiplied together and 2 y's multiplied together, and that checks out with what I started with. The next technique of factoring I'd like to go over is factoring by grouping. In this example, notice that we have 4 terms. Factoring by grouping is a handy method to look at if you have 4 terms in your expression you need to factor. In order to factor by grouping, I'm first going to factor out the greatest common factor of the first 2 terms, and then separately factor out the greatest common factor of the last 2 terms. The greatest common factor of x cubed and 3x squared is x squared. So I factor out the x squared and I get x plus 3. And now the greatest common factor of 4x and 12 is just 4. So I factor out the 4 from those 2 terms. Notice that the factor of x plus 3 now appears in both pieces. So I can factor out the greatest common factor of x plus 3. I think I'll factor it out on the left side instead of the right. And now I have an x squared from this first piece, and I have a 4 from this second piece, and that completes my factoring by grouping. You might wonder if we could factor further by factoring the expression x squared plus 4. But in fact, as we'll see later, this expression, which is a sum of 2 squares, x squared plus 2 squared, does not factor any further over the integers. Next, we'll do some factoring of quadratics. A quadratic is an expression with a squared term, just a term with x in it, and a constant term with no x's in it. I'd like to factor this expression as a product of x plus or minus some number times x plus or minus some other number. The key idea is that if I can find those 2 numbers, then if I were to distribute out this expression, those 2 numbers would have to multiply to give me my constant term of 8. And these 2 numbers would end up having to add to give me my negative 6, because when I multiply out, this number will be a coefficient of x, and this number will be also another coefficient of x. They'll add together to the negative 6. So if I look at all the pairs of numbers that multiply together to give me 8, so that could be 1 and 8, 2 and 4, 4 and 2, but that's really the same thing as I had before, and that's sort of the same thing I had before. I shouldn't forget the negatives. I could have negative 1, negative 8, or I could have negative 2, negative 4. Those also multiply together to give me 8. Now I just have to see if there's a pair of these numbers that add to negative 6, and it's not hard to see that these ones will work. So now I can write out my factoring as that would be x minus 2 times x minus 4. And it's always a good idea to check by multiplying out. I'm going to get x squared minus 4x minus 2x plus 8, and that works out to just what I want. Now this second example is a bit more complicated because now my leading coefficient, my coefficient of x squared, is not just 1, it's the number 10. Now there are lots of different methods for approaching a problem like this, and I'm just going to show you one method, my favorite method, that uses factoring by grouping. But to start out, I'm going to multiply my coefficient of x squared by my constant term. So I'm multiplying 10 by negative 6. That gives me negative 60. And I'll also take my coefficient of x, the number 11, and write that down here. Now I'm going to look for 2 numbers that multiply to give me negative 60 and add to give me 11. You might notice that this is exactly what we were doing in the previous problem. It's just here we didn't have to multiply the coefficient of x squared by 8 because the coefficient of x squared was just 1. So to find the 2 numbers that multiply to negative 60 and add to 11, you might just be able to come up with them in your head thinking about it, but if not, you can figure it out pretty systematically by writing out all the factors, pairs of factors, that multiply to negative 60. So I can start with negative 1 and 60, negative 2 and 30, negative 3 and 20, and keep going like this until I have found factors that actually add together to give me the number 11. And now that I look at it, I've already found them. 15 minus 4 gives me 11, so I don't have to continue with my chart of factors. Now, once I've found those factors, I write out my expression, 10x squared, but instead of writing 11x, I write negative 4x plus 15x. Now I copy down the negative 6. Notice that negative 4x plus 15x equals 11x. That's how I chose those numbers. And so this expression evaluates as the same as this expression. I haven't changed my expression. But I have turned it into something that I can apply factoring by grouping on. Look, I've got 4 terms here. And so if I factor out my greatest common factor of my first 2 terms, that's, let's see, I think it's 2x. So I factor out the 2x, I get 5x minus 2. And then I factor out the greatest common factor of 15x and negative 6. That would be 3. And I get a 5x minus 2 again. This is working beautifully. So I have a 5x minus 2 in each part, and so I put the 5x minus 2 on the right, and I put what's left from these terms in here, so that's 2x plus 3, and I have factored my expression. There are a couple special kinds of expressions that appear frequently that it's handy to just memorize the formula for. So the first one is the difference of squares. If you see something of the form a squared minus b squared, then you can factor that as a plus b times a minus b. And let's just check that that works. If I do a plus b times a minus b and multiply that out, I get a squared minus ab plus ba minus b squared, and those middle 2 terms cancel out, so it gives me back the difference of squares just like I want it. So for this first example, if I think of x squared minus 16 as x squared minus 4 squared, then I can see that's a difference of squares, and I can immediately write it as x plus 4 times x minus 4. And the second example, 9p squared minus 1, that's the same thing as 3p squared minus 1 squared, so that's 3p plus 1 times 3p minus 1. Notice that if I have a sum of squares, for example, x squared plus 4, which is x squared plus 2 squared, then that does not factor. The difference of squares formula doesn't apply, and there is no formula that applies for a sum of squares. There is, however, a formula for both a difference of cubes and a sum of cubes. The difference of cubes formula, a cubed minus b cubed, is a minus b times a squared plus ab plus b squared. The formula for the sum of cubes is pretty much the same. You just switch the negative and positive sign here and here. So that gives us a plus b times a squared minus ab plus b squared. As usual, you can check these formulas by multiplying out. Let's look at one example of using these formulas. Y cubed plus 27 is actually a sum of 2 cubes because it's y cubed plus 3 cubed. So I can factor it using the sum of cubes formula by plugging in y for a and 3 for b. That gives me y plus 3 times y squared minus y times 3 plus 3 squared, and I can clean that up a little bit to read y plus 3 times y squared minus 3y plus 9. So in this video, we went over several methods of factoring. We did factoring out the greatest common factor. We did factoring by grouping. We did factoring quadratics. And we did a difference of squares. And we did a difference and a sum of cubes. In more complicated problems, you may need to apply several of these techniques in order to get through a single problem. For example, you might need to start by pulling out a greatest common factor, and then